Well, next talk is Dr. Vincent van Wingerden from the Classiq company. The title is High-Level Quantum Application Design with Classiq. Please.
Thank you. So welcome everybody. My name is Vincent van Wingerden. I'm from Classiq, where I'm responsible for our strategic partnerships. There we go. Thank you. So Classiq is a company currently with roughly 70 employees. Most of them are engineers, and we're based all over the world. I'm based in Amsterdam, but our main office is in Tel Aviv, but we also have offices in Japan and in the US as well. And later I will say, but we have a lot of different types of customers, both in academia as well as commercial companies. And one thing that is pretty cool that is just announced is that we are actually opening an office in Italy as well. So that is one thing that we are very excited about, that we're going to expand our footprint here in Europe much more. So what is it that we do? So we have learned a lot about quantum technologies and how we're going to scale up physical quantum devices. But then the question is, how are we going to program these devices to actually have the useful programs run that we actually expect from these computers? So how are we going to efficiently program Shor's algorithm? How are we efficiently going to program Grover's or whatever we want to program? If we look at the way how we program quantum computers now, it is by what we call gate-based programming. So people are putting gate by gate or blocks of gates into a quantum circuit, and those gates together create your quantum program. So if you're familiar with this approach, you are very familiar with probably the most left picture. So a few gates. And this is something that basically anybody who has done a course on quantum computers will be able to create. It will become a bit more challenging when we go to the picture in the middle. The circuits becoming larger, and therefore also the possibilities that you as a programmer have become larger. So that means that there are different ways of implementing the exact same algorithm. And then it is up to you as the programmer to choose what is the most efficient implementation. And the trick here is that is not a single good or bad question. The answer will be different depending on the quantum computer that you're going to execute on. So that means if we're going to execute on a computer of quantware, the most efficient circuit that will implement a specific functionality will be different than a computer that is made by Seq or by anybody else. And if we're going to look at the size of the programs that we're going to need to have quantum advantage, those programs are so big that we are very sure that a human will never be able to have this gate-based approach and actually write the most efficient quantum program. So we need some sort of way to automate that for us. Luckily, this is a problem that we as humans have faced before, because when we were talking about the ENIAC before this, we were also programming gates, just like this. Luckily, we solved that with a tool called EDA, Electronic Design Automation, and high-level programming languages and compilers. So that is what we are proposing as well, specifically for quantum computing. So at Classiq, we have developed the first high-level quantum computer programming language, as well as the first compiler for this quantum computing language. So what is a quantum computing language? What makes it high level? So firstly, we do not focus on how you implement something. So you do not focus on the gate-based implementation. You focus on the functionality. What do you want to implement? Imagine now if you're programming in Python or in Java or in C, you're just writing a function. You don't care how that is implemented. The compiler does that for you. So that is something that we want to achieve as well. And once you have achieved that, you're able to develop a lot faster. So because you don't have to worry at this low level, you can just write high-level functionality and worry about how that is implemented later. With that, we can also believe that more people will be able to actually code for quantum computers. Now the people who are able to code for quantum computers are a relatively small group. They mostly have a PhD in quantum computing, and we want to expand that group. We want to make sure that domain experts who are not experts in quantum computing can also use quantum computers. So that is why we believe with a high-level language, we can bring in experts from all different fields like chemistry, finance to actually use quantum computers, because they do not need to know at gate level what happens. They need to know this at a higher functional level, just like they're modeling currently in Python or in any other language. So the language we're proposing is called QMod, which stands for Quantum Modeling Language, but obviously we also have a Python SDK that can be used. So let's say we have created an amazing program, a functional program in our language, in QMod or in our Python SDK. We somehow still need to create a gate-based circuit to execute that. For that, we are using our compiler. And our compiler takes two inputs: the quantum program that we have developed, so the functional program, as well as the characteristics of the quantum computer that you want to execute on. So you'll say, well, this is the function, and this is the topology of my quantum computer and the gates that my quantum computer has. And then our compiler will create the most efficient gate-based implementation possible for that specific function. The nice thing here is if you switch from computer A to computer B or from a simulator to a computer, you do not need to manually recode anything. The only thing you need to do is recompile with the new configuration. Or maybe if you have more qubits available to you, you don't have to think, how can I take advantage of that? You just say, well, recompile with this new configuration, and there you go, you're off to the races. And we believe that this is necessary to actually have quantum advantage for everybody, because coding in a low-level gate-based language is simply not scalable. And our platform also shows that using a compiler has way better performance than people are doing themselves. So this is a comparison between Qiskit and Classiq for a specific algorithm, namely QPE, quantum phase estimation, which is a subroutine on many algorithms like Shor's, but also being used in, for example, chemistry. We show that with this approach, we can create a lot more efficient programs. And we have created a complete flow for every single programmer, an online flow that they can basically go from modeling, compilation, visualization to execution in one environment. And this is what we call our Classiq platform. And it will allow anybody to execute and create code for anything online. Of course, if you prefer to use things on your laptop, that's fine with us as well. But not only online. We know that quantum computers are currently not the only target. So we need to integrate with HPC centers as well. Which HPC centers are the ones who are hosting quantum computers. And we know that we need to work together to develop hybrid algorithms using both the power of quantum as well as the power of classical computers and GPUs. So that is a complete stack that we're offering, from applications all the way down to hardware integration between QPUs as well as the classical hardware. Next thing, we need to make sure that people onboard as soon as possible to this new quantum world. So with that, we have created the largest quantum library that is available. In this GitHub repository, we have over 20 base algorithms already implemented. They're open source, anybody can look at them, and anybody can take it and compile them to a gate-based implementation. Next to that, we know that we need to make sure that we have these domain people coming in. So we're not just looking at base quantum algorithms, because it might be difficult for somebody in finance to take a quantum amplitude estimation algorithm and turn that into an option pricing algorithm. So we have done that for them. So we have more than 30 industrial algorithms already ready in the library that anybody can use right away. And there's also a lot of implementation of papers. So if there's new algorithms coming out on papers, we're trying to publish these as well. Then education. We need to make sure that everybody understands quantum computing, and therefore we're offering workforce education, both professional workforce education as well as courses in universities. So we are offering these to make sure that, yeah, we get as many people as possible in this whole cycle of quantum computing, and we're not waiting any longer, and we have complete courses from primitives to, yeah, running algorithms on real hardware. And then, so I'm not sure how I'm in time, some quick use cases of some customers that we are working with. We're working in basically any domain, from automotive to telco to healthcare and anything in between. And one of the coolest examples I like a lot is doing together with Rolls-Royce, who are using our software to create, simulate airflow inside of their airplane engines. So there's a specific algorithm called HHL that they can use to model these airflows. It's a little bit more explained a bit simplistic, but that's the goal, what they're trying to do. And they're using our platform to create these circuits, because creating these circuits is something that's so complex that with the ability of abstraction, they're able to create more complex circuits. Together with BMW, we're doing the optimization of some of their parts inside of their cars to make them more efficient. And this algorithm actually is one of the most complex collection of algorithms that we ever created. So they're using not just a single algorithm like QAOA or HHL. No, they're using them together. And for some people who then think, well, the one is digital and the other is an analog encoding. So within that, there's also transversion for quantum systems. So it is one of the most complex algorithms that we have ever created. We're doing quantum machine learning for brainwaves together with Igilov to understand better how can we classify specific signals that are coming from brainwaves. And this is a very cool use case that we did together with Intesa Sao Paulo. So they have a very capable team of modelers in financial derivatives. So in this case, rainbow options. And we help that team to go from very advanced modelers to also quantum modelers. So within a year of the projects, they have actually published the first paper to use quantum computers for pricing complex derivatives, in this case, rainbow options. I thought Simone is not still there, but I thought I'd put this in. This is what we did work together with AWS to do portfolio optimization for Citibank. So there's many different use cases that we can do. And with that, I wanted to say thank you. And if there's any questions, please let me know.
Thank you very much for your presentation. Please, questions and comments.
Thank you for a nice presentation. I think the work you're doing is really necessary. My question is about open source. So what's your attitude about open source? Because you want to become the one to Microsoft, or you are open to wider community? Yeah. What's your business model in that case?
Yeah, that's a very good question. So our library is open source. Anybody can use it. A large part of our implementations in our SDK is open source. The only thing that is closed source for now is our compiler itself. So that is a technology that's closed source. We have written a paper on how we implement it. that specific compiler. So you can read how we are doing it, but for the moment, that part is closed source. But the implementations on top of our compiler, those are all open source, and yeah, you can have a look at it.
Okay, well, another question or comments, please? No? Okay, thank you very much for your presentation. Thank you.